Welcome to part 3 of lecture 17, covering section 18.5 on the topic of center of mass. Okay, so we have seen one simple example so far with a system of discrete particles, and now in example 2, we're going to look at another system of discrete particles and find its center of mass. In this case, it is a system of 3 particles. Okay. So the first thing, let's read the problem. So we see we have 3 masses. They all have different values, m1, m2, and m3. 2 of them, m1 and m2, are located on an axis, and m3 is located at an angle, which here are given, as you can see here. m3 is in the 3rd quadrant, and the other 2 are kind of on axes that divide the 4th and 1st and 1st and 2nd quadrants, respectively. All right, so let's go ahead and kind of look at our first setup here. So the first thing that I'm showing here is some angles that we're going to define, and where the center of mass is going to be, kind of where we might anticipate it to be, which is a good idea. It's hard to know for sure, but since n3 is significantly larger, we should probably anticipate that the center of mass should get pulled closer to m3, and indeed that's the case. And then after the calculation, you will see that this is a pretty good guess. Fancy that. We're going to find an angle beta and an angle phi. And obviously theta is given in the picture. Okay, so the first step is we're going to find the x center of mass. I want to do that very much like in example 1 from these notes. And we'll see that we take each mass, multiply it by its x location, which of course for m2 is going to be 0, because m2 is on the y-axis. And for m3, we have to take a coordinate to get its x location, a coordinate of its displacement vector. Displacement vector is the one that's given here. Okay, and so then we get a value of negative 0.6084, working with the 4 sig figs in this problem. All right, so that kind of, again, matches up with the location that was shown in the picture. So taking a look at the y center of mass, we can do something quite similar. Take into account the locations. In this case, m1 doesn't have a y coordinate. And what we get there, and of course, as we did the first case, dividing by the total mass, as you always do, we get a y location of our center of mass that is also negative. Okay, so indeed m3 ended up pulling the center of mass closer to it and down into its quadrant. Okay, so that was again very similar to example 1. In part B, we're asked to take this information and put it into a vector. All right, so we see here that the first thing I do, actually to finish up answering part A, is I find the magnitude of the displacement vector, and I find it to be negative 0.6228 meters. So that would be the length of this vector here, okay? The one that would be going from the origin to our location of center of mass shown in green. Okay, and then in part B, that's where we're asked for the angle that the center of mass vector makes with the positive y-axis. Okay, so that would be the angle phi, because the positive y-axis is of course this way, our displacement vector is this way, and so the angle between the two would be going to phi. Okay, and actually you can see that my phi is slightly not drawn correctly because it should be going actually from here to here. It extends a little bit too far down. Okay, because it doesn't go from the vector for mass 3 to the positive y-axis, but instead from this vector to the positive y-axis. But you can see in the calculations that I calculate it correctly. So I take 90 degrees and then add beta. Beta is just this small vector here, and then that will give us the vector that we were asked for. In order to find the angle of beta, I use inverse tangent with the y component of the center of mass divided by the x component of the center of mass, because that would be opposite over adjacent, because going back up here and looking at the picture, this would be ycm, and this here would be xcm. All right, so we can then sort of imagine, right, this one here, ycm, and this one xcm. And so, of course, tangent will get us the angle we want. And so when we make that calculation, we get 102 degrees, showing us that beta is about 12 degrees. So in other words, that vector is about 12 degrees beneath the y-axis. Not very far, right, because the other 2 masses do pull the center. So it's not, way down close to m3. Of course, if m3 was much larger, then the center of mass would be much closer to its own center. Okay. All right, so that is example 2. Working more with discrete center of masses like in example 1, but including the idea of taking a vector to represent that center of mass and finding its angle relative to a particular axis. Okay, so in question 1, we have a conceptual question here, and we're told or asked that a machinist starts with 3 identical square plates, but cuts 1/4 from one of them and 2 corners from the second, and 3 corners from the third. Rank the 3 plates according to the x coordinates of the center of masses from smallest to largest. Okay, so tied for smallest is going to be number 1 and number 3, so they each get the rank of 1. And that's because if we think of what's going on with number 3, where 3 corners are cut, those 3 corners, well, the 2 corners shown here with x's through them cancel out by symmetry in terms of affecting the x center of mass. Because whatever effect this missing mass had on the x center of mass, this one has the equal in magnitude and opposite effect on the x center of mass. So these two are tied. For the greatest, so with the smallest rank, the greatest x value of the center of mass would be number 2, because over here the center of mass would get significantly pulled in the x direction because there's a lot more mass over here because of all the missing mass on the negative x side. Okay, so there's a good way to visually see the center of mass and the effects of removing or adding mass, in this case, of course, removing. Okay, so let's move right on to example 3. Okay, so example 3 represents a shift from dealing with discrete systems of particles and finding the center of mass of that discrete system to a continuous object. So this is an object with a continuous mass distribution. Okay, so let's take a look at how this problem differs. And of course, this problem, unlike the ones that we've seen so far, will require calculus. So the first thing, let's take some labeling into account here. So you see here that I have labeled that dm is the mass element. And we have a Greek letter here, the Greek letter sigma. This represents linear density. That's a good fit for this type of problem because it's a rod. And so although the rod would have dimensions in y and perhaps into the page and the z-axis, we don't care about them because it's symmetric. It's maybe a cylindrical rod or a square rod. But the important thing is that that's not going to affect the center of mass. We weren't asked for the center of mass in those axes. And so we only care about the distribution of mass along one axis. Hence, instead of having what would be typical density, which would be kilograms per cubic meter, instead we just have kilograms per meter. Okay, so it's sort of a simplified version of density. And the idea here, this equation, shows that the mass element, dm, is equal to that linear density times dx. Okay, but that makes sense. Unit-wise, of course, we would have kilograms over here and kilograms over here after we multiply mass linear density by dx, which is just measured in meters. And essentially what it's saying is that that little mass element, which is infinitesimally small, has an infinitesimally short length, dx, and within that infinitesimally short length, there is the density. Okay? Now, the first part, part A, we're going to deal with a density that is consistent with a uniform density. So the idea that as we go along the length, lambda doesn't change. So that's a uniform rod. But what if the rod is getting thicker or thinner, which would be effectively affecting its density? Or what if it's just made of different material, so it gets denser and denser as we go further down? Well, then we would have a linear density that itself is a function of x, which we can deal with quite elegantly just with the integration that was already defined in the equations on these notes. Okay, so let's look first at the uniform density case. Okay, so again, we're only be dealing with x here. There's going to be no y center of mass. So we'll just deal with the x center of mass. We'll write out its definition as 1 over the total mass times the integral of integrating mass elements and their coordinate x. Okay. Then the first thing we'll do is we'll make the substitution that is shown in the figure. So that means we're going to replace dm with lambda dx. Okay. And that is a very, very common replacement. So with all these center of mass problems, with continuous ones that require calculus, you will be doing that type of differential substitution every single time. And when we deal with, later in a couple weeks, when we deal with with not the center of mass, but the moment of inertia, a very similar concept, we'll be doing that again. So it's a good thing to pay attention to. Okay, so the last thing I'm going to do is I'm going to take a look at this arrow right here, this black arrow that says density is a constant. Okay, since density is a constant, our lambda, that's our linear density, is simply the total mass divided by length. Because at any point it doesn't change. So we're just that's always going to be true for any uniform object, in this case a uniform rod. Okay, so that allows us to do some great substitutions because our m over l are constants. So the m over l come out, allowing our m's to cancel. Then we're going to go ahead and integrate x dx over 0 to L, because we're integrating it over the entire length. You can see here that this represents the end of the rod. It's kind of offset slightly, but this would be x equals L, the very end of the rod. Okay, you can see L over here. Okay, from there to there. And again, this is, as we see, as now we're about to solve this integral, you can see the crucial importance of our substitution for dm, because you can never integrate over dm. You have to define m in terms of some variable over which you can integrate. Okay, and of course dx is just that. So then when we do our rules of antiderivatives, our x becomes a 1/2 x squared. We'll evaluate it from 0 to L, and when we do our upper limit, we're just going to get our L squared over 2. One of our L's cancel, so the second L cancels like that, and we get our final answer, which is just L over 2. But of course it is, because it's a uniform density rod, so of course its center of mass is exactly in the middle. All right, so then we got a result that makes sense. Good sign. Okay, now in part B, things are going to get a bit more interesting. This is really the utility of this integral approach to continuous objects, rather than just proving something that we would already know in this case. So in part B, we have if instead the rod has a linear density that varies with length, and it's going to vary from a value of L naught at one end to a value of 2 L naught at the other end. So in other words, it gets twice as dense as you go from the origin to the far end. Okay, in that case, where is the center of the mass of the rod located? Right? Where is it located along the x-axis? Well, we should certainly expect that when we had a uniform density and it was right in the middle, well, now that it's getting denser, the new center of mass should be closer to the denser end, right? Because right here it's much denser. Okay, so let's look about how we would do that. All right, so we need a function for the linear density as a function of x, and it turns out that that function ends up being just lambda naught times 1 plus x over L. So you can ask about this in office hours or in online chat. And essentially the idea here is that this comes simply from thinking about the equation of a line, because essentially we have 2 points on the line. We have 2 density points. We have a density at one end where x equals 0, and we have another density at the other end where x equals L. If you use those 2 points and use the point-intercept format of finding the equation of a line, you get this. Okay, and of course it makes sense, because if we plug in x equals L, then we'd have L over L, which gives us 1. And so then we'd have 1 plus 1, or the density at x equals L is 2 times lambda naught, which is exactly what it should be at the far end, where it's twice as dense as at the origin. And when we plug in x equals 0 for the origin, then we have 0 over L, or just a density of lambda naught, because that's the original less dense end. Okay. And note that this time we will need 2 integrals. So we need one integral run, which will be the x center of mass, the one that's defined. But here's the thing. Anytime you have a non-constant density and you're given a density function or asked to find one, like we were here, then you have to do a second integral, which is your total mass integral. Because otherwise, your answer is going to have lambda naught in the center of mass, in the final answer. But that doesn't work, because you need your center of mass to have units of meters. So you can't leave any other term in there. You have to do a substitution to get rid of it. And you'll see exactly what I mean in just a moment. Okay, so we'll do our first step to our first integral. And this is just the one we would expect, which is just the center of mass integral. And so we go through. We start with our x dm. We do a substitution where we replace dm with lambda dx. Then, now this is new, right? This didn't happen in part A. We're going to replace lambda with our function. Okay, so this is our density function as a function of x. There it is, right? It's a linear function. And so now we have our limits defined because I'm integrating over x from 0 to L. All right, and I'm ready to actually solve the integral. So we go ahead and do it up. So here I've split the integral into 2 parts just to simply show the rules of antiderivatives. So we do our x becomes an x squared over 2. Our x squared becomes an x cubed over 3. We have a constant L there that will be pulled out of the integral. And then we're going to evaluate from 0 to L. So when we do that, when we do all those steps and clean up our terms, combining our like terms, and that's an important thing. Anytime you do this integral, if your 2 terms ended up not having the same units, in this case, right, we're going to have L squared, because over here we plugged the L in for x, and over here we're going to have L cubed, but it's going to cancel with the L in the denominator, which will give us another L squared. So that means that both these terms have to have the same dimensions. And it's a red flag if they didn't. It just means you made a mistake with one of your antiderivatives or you lost a term somewhere. So it's always a good way to check your work. So this might look like the final answer for the x center of mass, 5, 6, L squared over m, but here's the whole issue. It still has m in it, and it shouldn't be in terms of m, it has to just be in units of meters, and it still has the original density, which we don't know. We don't know what lambda naught is. We don't need to know, it will cancel out. But now we see the necessity of doing our total mass integral. And this whole purpose of this total mass integral is just to express the mass in terms of lambda naught. That's it. Okay? So, and since xcom needs to be in terms of L only, as I said, we need m, the total mass, in terms of lambda naught and L. So we set up the total mass integral. I'm going to do a substitution of dm, which of course will just be lambda dx. I'm going to express lambda as the function that we defined earlier and explained earlier. Then I'll go ahead and do the rules of antiderivatives. And so then I get that my total mass is 3/2 lambda naught times L. So that's m. That is m in, it's got units of kilograms, and it's the total mass in terms of lambda naught and L. Okay, so then I will take that expression for m, substitute it in here, as we see, right? So the 3/2 lambda naught L replaces the m. Okay, see? And then cancel out the lambda naughts, cancel out one of the L's, and we get our final answer, 5/9 L. And that answer makes sense because it's closer to the end. It's closer to the denser end. It has a value larger than L over 2 because the way we defined our system, this is L. That's the end of the rod. Okay? So that's a good example of a non-constant density and just a continuous object in general. Okay? So definitely this is the much more trickier, much more mathematically demanding type of example when it comes to center of mass in comparison to the discrete systems. So one you need to be paying attention to and getting some practice with, and please ask me if you have any questions. Okay, so I just want to quickly show one last example. This is a cone. Okay, so here we're going to just do kind of the same sort of setup. We have dm, which we're going to define here in terms of density and volume. So here we're actually using volumetric density instead of linear density. We're going to use the definition of the center of mass for a solid continuous object. Okay, in this case we only care about the z center of mass because there would be symmetry in the y and x axes. So that we can then easily imagine, because that symmetry, there's nothing to pull the center of mass to this side or in the x direction. So it's only going to get affected by the z direction. And of course, we're going to expect it to be closer up here somewhere because as the cone comes down to a point, there's less mass. Okay, so then we're going to consider here that dm is just a mass element. Okay, and then looking at the total mass integral shown here, I say that is not a concern because the density is constant. And that's the whole point, right? Now the cone has its own trickiness that you'll see in the process in just a moment. But we definitely don't have to do the same approach that we did for part B in the previous example. Again, because lambda, or in this case, rho, is a constant. And density is a constant. And lambda being linear density, rho, volumetric density. But the important thing, density is constant, no total mass integral. Okay, so then I just go across with the center of mass integral, make the same substitution for dm in terms of rho dv. So rho is the density of the cone. So rho would just be the total mass divided by the total volume, mass over volume. All right, so then we'll make that substitution. So now we have the interesting part here. I'm going to replace dv because our substitution here before it would be lambda dx, and then once we had dx we were done, right? It was in this case maybe lambda dz because then we're ready to do our integral. But of course when I did the substitution here, I went from dm, the mass element, to lambda dv. Well, what is dv? It's a volume element. Well, the volume element isn't ready to integrate either because it's not in terms of z. So that's what we have to do. We have to express the volume, this little disk here, in terms of z. Well, it turns out that that's an interesting process, not necessarily an intuitive one, but when you see it, it should make sense. That we take the area of the disk, okay, because that disk has a radius of r. Now, r is a variable. And so we're going to take that lambda r squared as the cross-sectional area of our little infinitesimally small disk. Okay, and an infinitesimally thin disk because dz is the thickness of our disk, and that's what we're integrating over, little tiny slices of our disk. Okay, and so then we have to do a substitution though, I should say our third substitution, because r, that radius of the disk, changes because of course when you have a disk closer down to the tip, it's small, right, infinitesimally thin because dz is always going to be very, very small, but the cross-sectional area varies as we go up the cone. So what we do is we use the idea of similar triangles to express r in terms of the maximum value, the final value of the cone, okay, divided by h, the height of the cone, multiplied by z. Okay, and we see when r equals 0, z equals 0, and when r equals big R, that's the variable r equals the maximum radius r, z equals h. Okay, so we have an expression that makes sense, and hopefully you see where it comes from triangles. Okay, so we'll put that substitution into our integral, which is almost ready to solve. We'll factor out our constant volume, factor out other constant terms like pi and r squared and h squared, because those are all constants. And then we finally have an expression for z cubed, which we're going to do the rules of antiderivatives for. We're also going to replace the expression v in terms of the actual definition for the volume of a cone. This is one you would really look up, and it ends up being pi r squared h over 3. I won't ask you to prove the volume of a cone, and if it was on an exam, I would give it to you because it's not a well-known volume expression, unlike, say, the volume of a square, which is, of course, just, x cubed. Okay, so let's replace v with that expression, and you can see why we want to do that, because now we're really going to be canceling out a lot of our terms and getting an expression that doesn't have leftover constants like the big R or h once we evaluate our limits of integration from 0 to h. And you can see we have a z to the fourth, but of course it won't remain a z to the fourth because we're going to have h to the fourth and then cancel with h squared and another h. And we get our final answer, right? It should ultimately be in terms of h. It has to be, because just like when we were doing the center of mass for the rod, our final value had to be in terms of the overall length of the rod L. Well, if we're finding the center of mass along the z-axis, the height axis for the cone, then our value has to be as a fraction of the total height h. And when we do that, we see that the cone has a center at 3/4 of h. So the center of mass of the cone is right there, 3/4 of the way towards the thick section of the cone, right? The top of the cone in this case, because our cone is upside down, right? If it was the base, it'd be 3/4 of the way towards the base. Okay, so that's our final example for the notes, and our second example of a continuous distribution that requires calculus. Hopefully you kind of see the utility of center of mass. That will become more evident as we put it to use in rotation problems, but at least you'll see how to calculate it. Thank you.